All right, let's turn our attention to nitrogen nucleophiles. And under acidic conditions, aldehydes and ketones react with primary amines to form what's called an imine. So I just want to remind you that a primary amine is when we have an R attached to our nitrogen, and then we have two hydrogens. So again, primary amine has two hydrogens attached and an R group. So when we take our aldehyde or ketone and we treat it with a catalytic amount of acid, in this case, this primary amine, this is called methylamine, and I know we haven't learned amine nomenclature, but this is methylamine, which is a primary amine, and of course we're losing water here. We form a new functional group called an imine, and as it says here, the reaction requires acidic conditions to work, so we have a catalytic amount of acid shown here, and we form our imine. And imines are also sometimes known as Schiff bases. So Schiff, an imine is also a Schiff base, which is named after somebody named Schiff. Anyhow, so you need to know what an imine is, and in an imine, keep in mind there's a carbon-nitrogen double bond in there. And the mechanism of the imine formation is shown here. Now, I'm not going to quiz you on this a ton, but you should go over it. And what's interesting about the first step is the nucleophilic attack by the amine on the carbonyl. It's not a proton transfer to make an oxonium. And so we have nucleophilic attack by the amine, and then we have a proton transfer in the second step. And so this would be the protonated form of the amine here that's going to do the proton transfer. Then after a couple more proton transfers, you see here that we end up losing water. So we'll highlight that here. We end up losing water along the way. And I want to point your attention to the very last step here. And we'll come back to this in a second. But you notice that the very last step is deprotonation, removing the hydrogen that's attached to the nitrogen here to produce your imine. So notice that you lose water overall in the reaction. Notice that every step is in equilibrium, and also notice that there's a key intermediate here called a carbonylamine. And you should be able to recognize a carbonylamine when you see one. And you notice that the carbonylamine, this carbon has a hydroxyl attached to it, and it also has a nitrogen attached to it. So that is the carbonylamine, which is an intermediate in the synthesis. Now, something that's interesting about this synthesis is that we're using a primary amine. Okay, so we have our primary amine in the presence of a strong acid, and here they're showing HCl. Now, if you mix a primary amine with a strong acid like HCl, the equilibrium is going to lie exclusively to the side of the ammonium ion like this. And so even though we're under acidic conditions, protonation of the carbonyl was not the first step of the mechanism. It was the nucleophilic attack by the amine on the carbonyl. And the rationale here is that this ammonium ion is not nearly as acidic as the oxonium, and so it's not acidic enough to protonate a carbonyl, oxygen, but it is acidic enough to transfer a proton to the negatively charged oxygen in the second step. That means it's acidic enough to do the proton transfer in this step here, this being the second step. Now, something else that's interesting is that the pH of the solution is an important consideration during the formation of an imine, with the rate of reaction being greatest when the pH is right around 4.5. And you see that right here. It's right around a pH of 4.5. If the pH is too high, meaning if no acid catalyst is used, the carbonylamine is not protonated in the fourth step of the mechanism, so the reaction occurs more slowly. But if the pH is too low, meaning too much acid is used, most of the amine is going to be protonated to give ammonium ions, and therefore there's going to be no nucleophile left. Under these conditions, step 2 of the mechanism occurs too slowly. So as a result, care must be taken to ensure optimal pH of the solution during imine formation. Now, what's interesting is when we react our aldehyde or ketone with a secondary amine, and I'll just refresh your memory here. A secondary amine is when we have two R groups and only one hydrogen on our nitrogen, like this. So under acidic conditions, when we treat a ketone or aldehyde with a secondary amine, and of course when we remove water from the reaction mixture, we form what's called an enamine. So an enamine, so imine was with a primary amine, and enamine is with a secondary amine. And it says here, this reaction requires acidic conditions to work, and the mechanism is identical to imine formation except for the last step. So if you know the mechanism of imine formation, you know the mechanism of enamine formation. The only difference is going to be in the last step. Why? Because you can see we have no protons on the nitrogen to remove. And so just like the formation of the imine, the first step is going to be the nucleophilic attack by the amine. And then we form our carbonylamine along the way. We lose water. But then in the last step here to form the enamine, notice that we remove a proton from an adjacent carbon. We don't take it off the nitrogen because there's no proton on there. So that forms our enamine. And so we see the similarities between imine and enamine formation shown here. When you start out with your ketone or aldehyde, and here they're showing cyclohexanone, you treat them both with a catalytic amount of acid. Here we have a primary amine. Here we have a secondary amine. Okay, everything is the same in the mechanism up until the very last step. When we're working with a primary amine, the last step is a proton transfer off of the nitrogen. And when you're working with an enamine, the last step is a proton transfer off of an adjacent carbon. And sometimes students will laugh at my mnemonics, but these are things I've learned from students over the years. So sometimes my students, or somebody taught me this years ago, or one of my students told me, so it said primary amine and secondary amine like this. So they said the number 1 kind of looks like an I for imine, okay? And then for the enamine, if you can really use your imagination here, if you put a line like this, it kind of turns the number 2 into the letter E, so enamine. Okay, if you find this mnemonic useful, great, but if you don't like it, then just throw it away, I guess. Now, what's neat about the imine formation is you can do an imine formation, except instead of using a primary amine, you can use this molecule here called hydrazine. So if you have NH2, this is called hydrazine, and you can see the hydrazine here. So you can imagine this just being like an R group, okay? So when you react hydrazine with your ketone or aldehyde, catalytic amount of acid, and you remove water, you end up forming what's called a hydrazone. So this is called a hydrazone. And then an interesting reaction that you can do is you take the hydrazone and you just heat it up with some potassium hydroxide that's aqueous, and you end up removing the whole hydrazone part of the molecule, and you reduce it down to an alkane like this, and that's what we call the Wolff-Kishner reduction. Okay, it's kind of an old reaction, but people still use it. And if you're wondering, well, if it's so old, why is it so great? I'll tell you why it's so great, because you form nitrogen gas as a product. And where's that going to go? It's going to bubble out of the reaction mixture, and so it's going to drive the reaction forward based on Le Chatelier's principle. And so if you make a hydrazone, it's a great way to do a reduction, or the reduction of a carbonyl down to an alkane. Now, if you're saying, wait a second, you taught me how to do this using didn't you teach me how to do this using a Clemmensen reduction, using the zinc mercury amalgam? Absolutely, we could do a Clemmensen reduction. But remember, organic chemists usually like to know as many ways as they can to do the same kind of transformation. And what they would do is they would test them all on whatever molecule they're working with, and whichever one gives them the best yield, that's the one they would use. And so I'm not going to bug you about the mechanism of the Wolff-Kishner reduction, but it is shown here, and you can see it's nothing but a bunch of proton transfers. It's literally 4 proton transfers, but the important part to me for students is this part right here, is that you lose nitrogen, right, which is a gas, okay? So if you're wondering why I put the arrow going up like this sometimes, that just means it's bubbles. It's going up into the atmosphere. But if you want to write N2 gas and then subtract for loss of it, that's totally fine too. So there you go, Wolff-Kishner reduction. Now this is a real David Klein thing, the author of the textbook. Just one of his reminders is he says, look, you should note that there's all these similarities between these acid-catalyzed mechanisms, right? The formation of an imine, the formation of an enamine, even acid-catalyzed formation of an acetal, right? He says, one thing to note, when you're under acidic conditions, and this is really important, if you're in acidic conditions, everything should be either neutral or have a +1 charge. If you start drawing a mechanism in acid and you start seeing negative charges in your mechanism, you know, like Phil Collins said, something happened on the way to heaven. There's something severely wrong with the mechanism, so it's time to go back to the drawing board. So just keep this in mind when you're practicing your mechanisms. All right, predict the major product for each of the following reactions. Here we have a ketone. This would be cycloheptanone, and then we're treating it with ammonia, catalytic amount of acid, and we're removing water. So you can think of ammonia, you could think of it as being like our NH2, and then your R group is like a hydrogen, okay? You could think of it that way if you want. And so we're gonna form an imine in this case. So let me try to draw my best 7-membered ring. So we have our double bond to our nitrogen, and our R group in this case is gonna be a hydrogen. So there's our imine that we form. The next one, we also have a primary amine here. We have cyclopentanone. And so same thing here, we're gonna form an imine. And so remember, this double bond is gonna stay intact, right? Just like it did here, okay? But we're gonna replace the oxygen with a nitrogen. So we're gonna replace this oxygen with this nitrogen, just like we did in the previous example. So we're gonna start by drawing our 5-membered ring, keep the double bond intact. Now you have your nitrogen, and you're just gonna draw this piece, that's your R group, that's attached to your nitrogen. And so there you have it. And there is your imine, right? Primary amine, you end up with an imine, and if you work with ammonia, that will give you an imine as well. All right, the next one. Okay, so we have, this would be 3-pentanone. This compound here, if you have a hydroxyl on your amine, no joke, this is called hydroxylamine. It's actually mentioned in the textbook, okay? So you can think of the hydroxyl group as being your R group, like that. So same old thing. So we treat it just like we would a primary amine. So remember, the double bond is gonna stay intact, and we're gonna replace it, the oxygen, with this nitrogen. So let's pencil that down. So we have 1, 2, 3, 4, 5 carbons, double bond. There's our nitrogen, and our R group in this case is gonna be the hydroxyl group. And this functional group has a name. This is called an oxime, an oxime. And the next one, remember, this compound here, this is called hydrazine. And when we use hydrazine with our ketone, we're going to end up with a hydrazone. So we'll draw the hydrazone. That's going to result. So our double bond stays intact. Nitrogen, and our R group in this case is going to be our NH2 group. And so again, this is called a hydrazone. And what's neat about oximes and hydrazones. Now the hydrazone, we saw the Wolff-Kishner reduction, but with an oxime or a hydrazone, you can make heterocycles out of these. It's not covered in this class, but those are something you could do with those functional groups. All right, and here we have a secondary amine. So now we're dealing with a secondary amine and a ketone. So if we have a secondary amine, we're gonna make an enamine. And so let's draw what that enamine is gonna look like. So we're gonna have our 5-membered ring. Now we're going to have a single bond, right? It's not a double bond. We have a single bond to our nitrogen. We're going to have our 2 cyclohexyl groups intact. Those are our 2 R groups. And now our double bond is going to be here, okay? So that's where our double bond is going to move. So we'll put it like this. Maybe I could clean that up a bit. There we go. And so this is an enamine. All right, and for the next one, we got everything in the same molecule. This is called an intramolecular reaction, right? So we have our secondary amine here, and here's our carbonyl. And so if you think about the nucleophilic attack, right, the first step is the nucleophile is going to attack here. And so we should have 1, 2, 3, 4 carbons in the ring, and then we're going to have a 5th atom here. So we're going to end up with a 5-membered ring. So let's pencil that down. So we're going to have our aromatic ring like this. Then we're going to have our 5-membered ring, and we're going to have our nitrogen, which is going to be in this position. So I'll just draw it up like this to make it as easy as possible. So 1, 2, 3, 4. Oops, that's not very pretty. There we go. Maybe something like that. So our double bond is going to be at this position. So there's our double bond. Then we have the ethyl group coming off of the nitrogen like this, and then if we count over like this, 1, 2, 3, 4, 5, like this. On the third carbon, that's where we have that geminal dimethyl. A little trickier with this one. Just make sure you count your carbons very carefully.